I can see that. I definitely want to go into that.
All right, lecture 6.
Yeah.
And then next week is exam.
What?
Yeah.
Are you going to talk about that?
Which one?
The exam.
Exam?
Yeah.
If you guys want to, yeah.
Yeah. Okay, please.
Am I going to talk about the questions or the exam?
No,
like
no.
the format. Like give us like a rundown of what's gonna happen.
Nothing's really going to happen. You're going to have a lot of fun writing the answers down.
Wow, that's one way of putting it.
Did we? Okay, well, I guess I'll ask you.
We'll talk about the next lecture, yes. Yes. No, not in class. We could do it that way, but that just defeats the purpose of thinking.
No, I agree. Outside stuff.
Yeah. Good, good, we're in agreement. Okay, so lecture 6, skeletal muscular system. Any questions from last week? Or before that, or before that? No? Okay. So today I wanted to start off, because the skeletal muscle lecture is not as long as the other ones, I was trying to use some extra time today to talk about scientific papers, because the term paper will require you to do some research and cite the papers. So the question is, where do you find these papers? How do you find them? How do you know they're good or not? How do you read them and how do you cite them? Okay, so how many people actually have published scientific articles before? Or written up some research papers before in class? Okay, so jump in if you have any questions. So the thing is, the so-called scientific articles are a very diverse collection of papers that can't be muddled into one term. And that's why I want to dissect what we mean by scientific articles. So let's start with this then. Can somebody give me what they think a scientific article is? What is the definition of a scientific article? I mean, there's no right definition, but there are probably different definitions we all have. Just to get an idea. Yeah.
A lot of times they are papers that talk about experiments that scientists completed and the results of that experiment and the implications of it.
Right, dissemination of experimental facts. That's a very clear one, yes. Another idea of what a scientific article is? Yes, Richard.
Many articles are explanatory. That is, they explain scientific phenomena, or they may explain the results of one or more studies.
Right, so reviews,
Yes.
meta-analysis
Meta-analysis, reviews,
of literature.
teaching articles also.
So there could be that, a survey or a updated review of current literature. So those are called reviews. There could be opinion pieces where people disseminate their opinions of a certain topic. There could be conceptual papers, more theoretical approaches. So there are various types of scientific articles. Now, what do you want to use for the term paper is the question, right? Which comes to the question of what is the nature of the term paper, right? So I'll go through it more in detail later on when the time comes. But the term paper is in a way, an opportunity to compile all the basic facts, the knowledge that we collected in this class and you did research on, and then put it together to make your own hypothesis. And then support, in an evidence-based way, support your hypothesis and basically argue why you think X, Y, and Z is true or not. Or how the field should look at this problem in X, Y, Z way. So it's not just a literature review where you cite all the papers and the current studies. It's not a purely opinion-based article. It's not a conceptual paper per se. It's going to be a compilation of both or all of them. So get the facts, have an hypothesis on a certain topic, and then support your argument. Bless you. So the kinds of papers you want to read to support your term paper and any other scientific paper that you want to do is not solely based on a review or someone's opinion or some kind of conceptual paper. You want to get down to the actual research, what we call primary research articles, which are specific, like we just heard, experiments done to test a certain hypothesis. Okay, so let's see. So can somebody give me a reason why you don't want to use reviews solely to support your hypothesis? So for example, you're writing about aging and sleep. I just heard about sleep. And you started to support your hypothesis, which was X, Y, and Z, and the papers you cited were all reviews. Now, why would that be not a favorable thing? Yes. It's easy, but why would it not be favorable?
Because they're not like from the original work. They are reviewing a separate study.
Right. Yes.
It's kind of like a game of telephone, where it's like every time the
The
meaning
message
is
gets
changed,
relayed
like,
and
a little
changes.
bit.
Yes. True, both true. Right? And reviews are written by people, and therefore unintentionally they'll have some sort of bias added in, some form of opinions, in some cases a skewed view of the field, meaning they would prefer certain types of studies over the others and only discuss a certain part of the field. So you won't get a balanced view of what's going on, right? So reviews are good to get you into the field, an overall view of what's going on, and also every now and then to check what's the latest on the field. So you have to read multiple reviews. But it's horrible in terms of using it as a source to support your argument or support your hypothesis because of that reason. So don't cite reviews too much, especially when you have a specific point you want to argue. You should stay away from reviews. You can start off the paper with reviews saying this is the field and this is known, yada, 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 but you don't want to get into the specific argument and still rely on reviews. So primary research articles are specific, very, very specific papers that normally address one major hypothesis. So every paper will have or should have a major message, a core message it wants to disseminate. Some papers try to do more, and that becomes a little bad. Why do you think having too many messages in one paper, in one primary research article, would be not advised or ill-advised? Distracting.
Distracts from the
Right.
primary message of the paper.
Right. And by that we mean also there's a limited space you can disseminate your information. If you have too many topics in one paper, it's obvious that the depth of the analysis or the depth of rigor of the investigation cannot be high or strong because you're touching on too many things instead of one. So a research article really bases on one major hypothesis being tested experimentally to support that hypothesis. So observation, hypothesis, experimentation, and then you disseminate the information. So no paper for real alone will stand as proof of anything. There is no proof. There's only evidence, and that's why the interpretation is important. That's why you have to read the paper and also either agree with the authors or have your own interpretation or criticize it. Okay, so any questions on research articles? Yes.
The problem I see is the source and the quality, because the item that I submitted to you, I used the New England Journal of Medicine, I used the Lancet, I used Science, I do not use Scientific American because it's for the layperson. I went into the database, the USC Medical Library, and most of the articles are available on PubMed.
Yes.
But there are lots of journals that are published online, and they say they are peer-reviewed.
Yes.
But I'm not a specialist in molecular biology, so I cannot tell the difference between the Journal of Molecular Biology and the Journal of Organic Biology,
Right.
and they're all in the PubMed database at
That's
USC.
exactly what I want to talk about today.
Okay,
It's becoming worse and worse every year, too.
yes, because people can pay to get published.
The
and
predatory
it's
journals out.
junk science.
Yes, I will definitely. That's why I want to talk about this, because it is confusing. You get to the point, and then you have 5 million papers, and you don't know what to read and how to tell which one's the good one versus hastily done or even false. So let's start from this question then. What happens after a scientist or scientists complete a study? Right, you have a question. Why do we need sleep? Right, that's going to be a difficult question to answer in one paper. So you have specific questions, such as the effect of sleep on melatonin secretion over time for sleep quality, something like that. So you do a study, you do all these experiments, and then what happens? Have you thought about what happens after the studies have been done? So what do you think is done after the study is completed? Any ideas? Maybe somewhere on that side? Yes.
Do you mean some news, learns, research published?
So let's say they did all the measurements, and you have all the data now. The scientists have all the data. They did all the measurements, they put the people here and there and did all that. What do you do with those raw data? What happens to those measurements, observations?
Maybe I need to recheck their ways that they got the data and make
So they
sure.
they want to confirm
Yeah.
the quality.
Yeah, confirm.
They have
the
to do all the
quality.
quality check and all that, right?
And also check myself research base to make sure that nothing wrong with my
Right.
research. I think that is my.
Right, so you want to have all the data, make sure your hypothesis is still the same, make sure the data either supports or does not support the hypothesis, right? Good, so you put all that together. And then they make it into a paper, right? But what is a paper? It's basically a way to disseminate the discovery. So it's still processed by human beings, still driven by incentives and all that. So they will have an hypothesis, and sometimes it's not that difficult to try to fit the data into your hypothesis. So that's something we should talk about a little bit later. But basically what happens is they gather all the data, they make sure the quality is good. That's one of the first things you have to do. Put it together into an understandable form, and then they so-called publish it for everybody to see. And they take scientific journals as the outlet. Now, here's another key word here. What is a scientific journal? Like Richard was saying, Scientific American is not considered a scientific journal, so we'll talk about the different types of scientific journals and many, many other that are out there. So one key aspect of a scientific journal that we should be considering as something that you want to read or not is the fact that it has been peer reviewed, or if it hasn't been peer reviewed. So what does this mean, peer review? The paper the authors put together, they send it to a journal, editor picks it up, and then they send it to their peers, meaning people in that field who are experts who will read your paper and comment on it to say this is X, Y, and Z. And then that leads to a decision if the paper will be accepted and published in that journal or not, right? So peer review is a very, very important process. They're generally reviewed by multiple experts. The reviewers are generally selected by the editor based on their expertise. this is a little bit different now, but traditionally and still in most cases, the process is unidirectionally blinded, meaning the reviewers will know who you are, the authors are, but the authors don't know who the reviewers are. This kind of keeps the confidentiality and the peer review process more independent, not influenced by politics too much. But nowadays, there are cases where they open their names up, and when the paper is published, their names are also published, who reviewed, and also the review comments are also published, which is kind of interesting because you get to see what the actual comments were from the experts of the field, which adds to your analysis of the data on the paper. Okay, so generally comes back, and rarely in good journals do they say, great job, publish. Most of the times, it'll come back to the paper will come back to you, and the editor will say, well, the reviewers have X, Y, and Z problems with the paper. Fix it or do more studies to address their concerns. And then goes back, the same process, and in some cases comes back again, and they say, well, they're still not satisfied. And so this is a very, very rigorous process, not just a simple thing as, oh, we sent it out to the peers and they read it. That's not the end of the story. It's a very rigorous process. For PhD students, this is where they get really, in some cases, depressed because they thought the paper was out, and then another 6 months, another 6 months, another year. Some papers take over a year to publish after submission because of the revision. So it's a very rigorous process, and that's why it's important. This is an example of Isaac Newton. If he were to have published that paper today, he would have sent it to a journal, and the reviewers would have said, well, I'm not sure about the apple. He should do it again. So they'll say, well, make sure he does that 20 times to make sure every 20 times it happens. And so he's just sitting there waiting for the apple to fall, which is not that different from what actually happens in labs. You just do things and wait for the results to come out. And that's 6 months to a year and so forth. All right, so peer review, something you want to make sure the journal has before you start reading that paper from that journal. So what kind of journals are out there? The journals that we consider scientific journals can be divided into two large topics or categories. One is general topics journal, and these include Nature, Science, and Cell, and New England Journal of Medicine, and Lancet. And then the specialized journals, which examples for us would be Aging Cell and Cell Metabolism, Cancer Research, and so forth. So the difference is general topic journals cover everything, starting from discovery of the black hole all the way down to the influenza virus gene X, Y, and Z, to climate change and everything, right? So that will be covered by these journals. So you won't be able to find your topic as much in these general papers, but if you find something there, there's usually, typically broad impact, something that has a major discovery. Right? That's why people always talk about Nature, Cell Science, New England Journal of Medicine, Lancet, is because these journals will go for, that's our dean there.
Later.
Okay.
Pay attention.
Where was I? Yes. Go for paradigm shifting discoveries. That's the effect of the dean. And then specialized journals will be on topics that are more in your field of interest. So for us, something like Aging Cell will be mechanisms of aging. We will find a lot of papers in this journal. So you want to differentiate those two. Journals that are often ranked by an impact factor. So people love to score things, and these papers have different incentives for many, many different types of people in their career path. And so people love to have a numeric value. That's what people like to do. Like they have to rank things. We like to rank pretty much everything. And that applies to journals. And here it's done in many ways, but an impact factor is more of the commonly used traditional metrics to decide what the impact of the journal is. Meaning, do a lot of people read this paper and cite the paper, or is it something that you publish and nobody in the world read it other than you and your lab people? And well, my mom never read it. I don't want her to read my papers. That becomes a long discussion. Your mom is a conflict of interest. So a journal's impact factor is a measure of the frequency. So the calculation, the equation here, the way they come up with a number is the frequency which an average article in that particular journal has been cited in a particular year. So that's the basic component of the equation to derive the impact factor. How many times has that article been cited by other people in this given year is basically what it is. Yes?
That's difficult to find information, though.
Yes.
You have to research that on different websites and through different services.
So for well-established journals, you can just type in that journal on Google and then type impact factor, and most of the times it'll just pop up right away because people look for it a lot. But some obscure journals or the new journals, because they have to compile data over at least 3 years to have an impact factor, the new journals won't have an impact factor. Okay, let's see. Again, like I said before, there's different types of articles: reviews, research articles, editorials, news articles, featured articles, comments on other papers, opinions on topics, perspectives, and errata, meaning you made a mistake and you have to go back and say, well, we made a mistake. It's a correction. And USC, as many big research institutions do, have subscription to pretty much most of the journals out there that we will use. So by having a USC ID, you can get access to pretty much every journal that you can find.
Now, when I go into the Norris Medical Library
Uh-huh.
to do my research, I check the box peer-reviewed journals. Can I rely on that box?
Yes, probably yes, but you want to combine several approaches to, in a way, sift through the journals. Meaning, peer review is one thing, but that doesn't guarantee the peer review was done properly.
No, it certainly doesn't. And
Right.
I also shift by date, meaning I only go back the last year or two.
Yes, that would be advised too. But you also want to take into consideration impact factor too. Although impact factor does not mean everything, but it definitely gives you a direction or a sense of what the journal's establishment is. Because if a lot of people cited it, that means people read that journal, and the people there, when we say people, are basically people in the community, scientific community. So it's something that a lot of scientists around the world not only read the paper, but also cited it. And therefore, the impact factor has weight because it's been verified by the peers of that field. And if it's a major, broad impact paper, like I discovered DNA, then you'll be cited by not only people in your field, but pretty much everybody in the biological field or medicine. Okay, any questions here? No? Okay. What does this sign mean? Open access. I just showed you the answer. So most journals are expensive. How much? What do you think is the cost of an average article if you just purchase it online? You go around and you say, "Oh, I want to read this paper," and then they say, "Purchase." What do you think the price of one article is? Yeah, $30 to $60. So if you cited 10, that's $300 to $600. If you cited 100 papers, that's a lot of money for everything you write, right? So it's a problem, and not everybody is part of a big university like us, which subscribes to these journals as an institution. So basically, they have to pay. So there's a movement on providing science to the public for free, which is in the form of what we call open access journals. And basically, these types of journals provide the articles for free for everybody who has access to the internet. Okay, so these are scholarly journals. These are not popular science journals. These are actual scientific scholarly journals. that are available online to the reader without financial, legal, or technical barriers other than those inseparable from gaining access to the internet itself. Okay? So a lot of major publishers now have at least one or two different open access outlets or journals under their publishing group. So Nature has scientific reports, Nature Communications. One of the first journals to have started this is called PLOS. It's Public Library of Science, PLOS. And PLOS has different sub-journals or specialized journals: medicine, biology, genetics, pathogens, computational biology, neglected tropical diseases, and something called PLOS One, which is basically a general journal. And now we have something called eLife, and there are many, many more. These are just examples of it. eLife is kind of interesting because its birth started with a Nobel Prize winner who basically said, we want to boycott nature and science. We want to get away from that culture of everybody trying to publish in Nature and Science. And they made this new open access journal called eLife. Okay. So these are the scholarly journals we just talked about, but there are other magazines and journals that have the word science in it, and some people tend to cite that every now and then. And so I thought it was worth mentioning some of them and trying to figure out what the differences are. So Scientific American, as Richard just said, Popular Science, Discovery, these are things you can buy in normal bookstores in the airport and whatnots. But these are not scientific scholarly research articles. Okay? These are popular science magazines for the general public. These are written by professional writers, not scientists per se, who did the research. They often cite interesting research done by others. Right? They don't do their own research. They just go around. It's like a news article. They go around and find something interesting, and then they do a piece on that. And they're definitely not peer-reviewed. This is a for-profit journal, so they have writers that go through popular topics of that time, which might not be a topic of your interest. And therefore, it's sometimes, or most of the time, limited in depth and scope because it wants to target the general public. They're not going to talk about phosphorylation of a protein. They're going to talk about this protein does muscle, builds muscle. And then this is how they found it, kind of article. So definitely do not cite any of these papers or journals. Okay, and then to predatory journals. Okay, so publishing is a business. You make a lot of money out of it if you do it right. And so there are a lot of predatory journals that have recently gained a lot of traction. Some people get together and they make a journal. And then they say, you get emails saying, if you pay us $2,000, we'll publish your paper right away. And it's peer reviewed. And they say, and then we'll index it in these major outlets so people can find your paper. So this is something you definitely have to watch out for and definitely should not cite for many reasons we'll talk about. These are some of the hallmarks that you want to check if it's suspicious. Generally, you can just tell by how the paper looks. You take a paper, and if there's like 2 figures with 2 panels, and there are like 4 measurements each, likely it's not something you want to cite, right? So you want to see if there's a impact factor given. Of course, there's a caveat that the new journals that are still legitimate don't have impact factors, but generally journals should have impact factors. See if their websites are professional. Look for grammatical errors in their website. See if they use generic email accounts, or if they have their own journal email accounts. You'll get all these emails saying, oh, publish at our journal by editor@gmail.com. And you're like, huh? What is this? You have to have permanent identifiers such as ISSNs and DOIs, which are ways to label articles. And sometimes they charge very high or very low. Either way is suspicious. And there's no clear policy on copyright licensing or open access or retractions. So these are just some guidance to make sure that the journal that you're reading is not something of a fraud, an actual real paper that you can base on. So it's been a big topic. There are many, many articles on this. This was one in 2017 in Nature. Predatory journals recruit fake editors. So this is kind of funny. This is the part that gets really funny. A lot of weird stories I hear. Let's see. I'll skip on this. I'll just tell you some stories. So sometimes there are people who say that they were asked to review their own paper. You submit a paper and the editor sends an email to you saying, can you review this paper? And it turns out to be your paper. Basically, the editors are not really up to the task because they're fake editors. They're just people who just hang out there and have a title slapped on as an editor. Sometimes it's peer reviewed by their friends. Basically, they're not experts in the field, but somebody who will give you a favorable review and a green light to go and publish it. So when something happens, they can say, oh, we peer reviewed it, and the reviewer said it's okay. And there are cases where they actually didn't review, and they say they reviewed, right? So these are all very bad signs. There are problems that are in the other direction. I'll just say this because it's related. There are now also authors who try to fake peer review, where you can recommend reviewers saying, oh, this person is an expert in our field and is a very well-known person who publishes here and there and has made these discoveries. So a very high-profile person in the field. So I recommend this person as a reviewer. And then they put someone else's email address. And so the review request will go to their friend instead of the actual person. And then they say, oh, this is a fantastic article, and you should publish this right away. and so there's both ways. There's problems both ways. So peer review is not a perfect system. In this case, at the editor level. So you can't really tell if it has been peer reviewed or if it has been peer reviewed correctly in these predatory journals. And that's the main reason you want to stay away from it. Has anybody read any found any, or had experience with predatory journals, fake journals? Not yet? Do you get emails about publishing? What's the most recent one that you got?
This was in undergrad.
Oh, okay. Yeah, you get some obscure emails. Okay. How do you select the articles then? It just sounds very daunting now, right? Do I just go for the high impact factor journals? Do I go for the 10 journals that I know? Or should I not cite the journals I haven't heard of? It's very, very confusing. So at some point, you do have to make a judgment call and decide for yourself if that paper or that article is worth citing or not. Let's see. Yes, okay, so this is just showing the number of publications. So publication is a business again, and this is how many publications have been increased in publication rate over the course of maybe 20 years or so, or 30 years. It just went up exponentially, which means back in this era, when you're writing a research article, you go to a library, you pick out books, and then there are like 20 books you want to cite. In 2014 or in 2019, you go online, and you type in aging and sleep, and you get like 500 pages of Google pages of articles. So the question is, well, what do I go with? Do I just follow what Google recommends, the first page? And Google follows a specific algorithm, which now the journals also target. So you get requests from editors. I got one recently saying, could you rephrase your abstract to include these words in this way, because that's how Google will search, find your paper, and put it on the front page. And so you can't really rely on Google searches either. That's also based on an algorithm that people made. So it's a daunting task. There's no answer. You just have to have some guidance. And this is some of the things that I use for myself, and I tell my students in the lab to try to focus on. you want to check scientific premise, right? If you find a paper that fits the bill for your hypothesis perfectly, you first think, well, this study has been done. It's perfect. But then you have to ask, well, what's the premise? So what does premise mean? If you want to start reading a paper and make sure, if you want to be certain that this paper is a good paper, you have to start thinking about premise. That's the first thing I would recommend. So what is premise?
Suppose.
Hmm?
Suppose.
Can you?
Suppose.
You suppose?
Yeah.
You suppose what?
I don't know.
It's okay. Elaborate.
I have no idea.
Okay. Anybody else? Premise? What is premise? Yes.
Is it like a strong evidence that support that scientific research?
Yes. So foundation. What is the foundation of this paper, right? So how do you tell if the foundation is good or wrong? Because if the foundation is wrong or bad, it doesn't matter how many experiments you do. It's basically castle built on sand. It's not gonna hold. So there are various ways of making your premise strong, and this you should also not only use it to decide on the papers, but also use it when you write your papers. It's the same thing. It's a two-way street. Your paper should also have a strong premise to begin with. So how does that work? Well, first you want to have very strong literature support. You want to know the literature of what's been done before, and don't reinvent the wheel. Make logical connections between different studies, and draw out a logical intellectual foundation for your paper. Saying X, Y, and Z studies have shown what, yada, 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 but then there are all these other studies also support the same notion, so therefore melatonin is important for sleep. That's established because of all these studies. Literature support, references. Or you should look at the data. You go through the figures, right? You get a paper and you saw the abstract and title. Okay, fine, this is something that I might be interested in. And then you look at the figures. And the figures are very weak in the sense that there's one piece of experiment done, or there's only 3 experiments in the entire paper. That's a very bad sign. They didn't really have enough data to say something strong. And then the rationale and logic has to be clean, right? Even though you have literature support and you have a lot of data, if there's no logical flow, it's just a collage of information put together. There's no logical connection to make something, a new conclusion or a new interpretation. So that paper basically is a bunch of experiments, a collage of experiments put together with no message delivered. Yes?
For scientific papers, does it mean more pages the better it is, or?
No.
Because more pages could relate to more graphs and more.
Okay, so yes and no. And I can tell you more a little bit later, but the baseline is the length of the papers are generally about the same. The journals will limit the word counts, right? There are some types of articles that require a lot of data information, and they are longer, obviously, and there are more figures, and so they will have more depth. But just because some of the top journals have that does not mean any journal that adopts that model will have the same. So you could do a lot of experiments that have no real connection to your hypothesis, and they can just put it in there as fillers, right? And so you read this paper, and it's more confusing because you can't make the connection yourself. Like, what is this? What does this have to do with this? So long doesn't mean it's always good. And also, people get wordy and they start throwing in their own ideas and concepts in the middle of a research article. Then it becomes kind of skewed. It becomes an opinion-based article rather than a fact-based article. I prefer succinct and clear articles with a specific message, because one article answers one question. It should never be a thesis that combines multiple questions. Then that's not an article. That's more of a thesis or encyclopedia. The next thing I look, and if I read this and I say, okay, it looks like there's a lot of good literature support that I agree with, and the data that they provide seems to be done substantially, and I understand their logical flow. Good. And then I look at scientific rigor. Did they really test the hypothesis, which is based on good premise? Did they test it with rigor, or did they just kind of, peruse it? Meaning, are there controls? If they compare something to something, is the compared control the right control? Are they comparing males to females, like exercise males and then sedentary females? Or are they comparing an 80-year-old man under dietary restriction versus a 6-year-old kid, right? What's the control here? Just because they had somebody who didn't do something as a control doesn't mean that's the right control. So, and this takes a lot of experience and training to identify what is the right control. And the experimental design kind of bounces off what I just said. It has to be clear and accurate. Complicated and cloggy experiments just because they're big and they're complicated does not mean it's good. Generally, experiments are much, much better when they're clear and accurate, simple experiments, rather than going through 25 loops. It's better to go with one model and test that directly. Right? So are the experimental designs clean and accurate? Is the methodology validated? So if I want to measure sleep, how do you measure sleep? When somebody says, taking melatonin increased sleep quality. How do you measure sleep quality? That's the methodology. Based on the methodology, you might not agree with their interpretation. If I told you my idea of sleep quality is somebody who snores, that's a good sleep. They were really tired and they really got a good night of sleep. But somebody might say, that's not a good sign of sleeping, that's actually a bad sign of sleeping. So the methodology can change the interpretation. And then the analysis. Did they get the data back? And like you said, you have to peruse the data quality and all that. But then did they just make a rapid surface conclusion after just seeing the data really quickly? Or did they dig into their own data? Saying, oh, but this could have happened for this reason and for this reason, and then study that further. So the depth of the analysis is also important. So that's scientific rigor. Then you got both down, and you're happy, like, oh wow, I can use this paper, great. And I read this paper and didn't waste my time. And then you're writing the paper, and it has to occur to you, well, are they skewed? Like, do they have a personal interest, or are they unintentionally skewing their interpretation? Are there other people in the field that think differently? Right? So is this topic something that is debated or confused in general, or do they also ask the question in a balanced way? So you got to ask that question. So you got to check the author list first, right? And we'll talk about that a little bit more. Are any of these people funded by the melatonin company? Are any of these people funded by the sleep drug company or mattress company, whatever it is? The conflict of interest. Do they own a company themselves, or do they consult for a company that sells this? So that's something you want to be focused on. And you want to get an overall understanding of the field. And this is where the review articles can help, right? Because you say, oh, I'm interested in sleep and aging, but I have no knowledge of sleep research. So I don't know what's going on. So you get a couple of reviews written by different people in good journals, and then get a sense of what's going on, right? So you have to have that idea. So if you have all three, not only can you decide on the right paper to cite and use to build your hypothesis or thoughts, if you follow these processes, you will write a good paper too, right? When somebody reviews your paper, they will say, oh, okay, this person wrote a nice article based on facts, strong logic, and they rigorously tested their hypothesis, and they're not paid by the company, and they understand that this is not the only view, so they have a balanced view. So conflict of interest can be found generally towards the end of the paper, under acknowledgments generally, but not always, but typically. So is the money coming from the government, other nonprofit entities like foundations, or is it coming from for-profit companies, like drug companies, that can use the paper to help sell their drugs? So check for all the authors. Okay, are they a consultant of something? Are they stockholders of a drug company? Are they this or that? And all that kind of stuff. Any questions here? Okay. So there's a lot of stories behind that conflict of interest. Oh, this is not that. This is a video. You might have seen this one.
Now, how the sugar industry paid experts to downplay health risks. Researchers have discovered documents showing the industry tried to influence scientific studies back in the 1960s. Early studies had found a link between sugar and fat and heart disease. But it now appears that the sugar industry paid 2 Harvard professors to point the finger elsewhere. At the time, it was not routine to disclose such conflicts. Marion Nestle wrote an editorial about the latest research in JAMA, the Journal of the American Medical Association. She's an author and professor of nutrition, food studies, and public health at New York University. Welcome, Marion Nestle. Let's start by a few.
Glad to be here.
Let's start with a few definitions. What was the Sugar Research Foundation?
Well, this was a trade association for the growers of sugarcane and sugar beets. It's now called the Sugar Association. So it's a trade group. Its job is to promote the sales of sugar and to lobby to make sure that nobody does anything regulatory to reduce the consumption of sugar. It's a trade group.
Yeah. So in all the years when we were being told that fat and cholesterol were the prime movers in obesity and early death and heart disease, it turns out that sugar also played a big role.
Well, it did. If you look at the epidemiology at the time, it was clear that both sugar and fat were risk factors for coronary artery disease. But these investigators at Harvard who were paid by the Sugar Research Foundation kind of cherry-picked the data and minimized the problems with sugar and maximized the problems with saturated fat. And that was exactly what the Sugar Association wanted them to do, as the documents show.
So the goal here was to sway public opinion in much the same way that the tobacco industry did.
Yeah, it followed the playbook of the tobacco industry. The #1 playbook rule is the first thing you do is you attack the science. You cast doubt on the science. Merchants of Doubt, the book and the movie, explain all that. And the Sugar Association was doing exactly that. It was trying to get researchers to produce research that would minimize a role for sugar and shift the blame elsewhere. And they were very frank about what they wanted, and the investigators agreed that that was what they were going to do. Pretty shocking.
If they could shop for experts for something like this, to find someone at Harvard who could tell them what they needed in order to preserve the industry, how do we know that hasn't happened, or maybe it has happened in other nutrition areas?
Well, it has happened, and the New York Times last year had a big investigative report about Coca-Cola's funding of the Global Energy Balance Network, in which they had emails that showed that there were very close associations between the researchers who were doing some of this work and executives at Coca-Cola. But it's very hard to get documentary evidence of this. But I do want to say one thing about it. It's not a simple matter of buying investigators. There were these Harvard investigators, at least one of them, was really pretty well known for his work linking fat to heart disease risk. And so he probably believed that that was what it was, didn't think that sugar was nearly as important, and believed that. So it wasn't as simple as the Sugar Research Foundation just saying, this is what we want and we're going to pay for it.
When you say it's not as simple, I'm going to ask you.
Right, so it's not that simple. You can finish the video on your own. So what the documents were saying was there's a specific location in New York, a specific building on a specific floor in a specific conference room where all the rivaling sugar producing companies got together, which they never do. And the documentation was like there was a full day of presentations by scientific researchers, and it was never, this is more of their interpretation. It wasn't like they were hiring people to say what they wanted to say. It was more like they were going through all the research and they were cherry picking the research and putting a twisted angle on it. So somebody like we just heard said, fatty acids might have a huge impact on this, which they never said much more than sugar, and sugar is not a problem. They never said that, but then the industry, they're very smart. These are really smart people. They're trillionaires, right? They will pick that thing and say, fat is a problem. No evidence of sugar. That's how you twist it, right? And so they blamed it on the fat industry, and the same thing was done with the protein industry, the meat industry, right? And so let me see if I'm going to talk about it. So if you go to, and this is really, really well done, lobbying, cherry picking scientific papers, supporting research that is favorable for their advertising, is done in such a strong way that you can't really tell that it's done until you look at the evidence. So for example, who reads labels when they buy food? Nutritional labels in the back of whatever container, right? So what do you see there? Total calories, okay, protein, fat, added sugar. But under the fat category, how many subcategories do you see in a lot of them now? 3, 4, I've seen 5, right? How many people actually understand the difference between monounsaturated, polyunsaturated, saturated, the general public? They don't. But somehow the regulatory agencies are going after fat. And then you go to sugar, there's total carbohydrates and then added sugar. They don't talk about simple sugars, complex sugars. Brown rice has the same amount of carbohydrates as sugar, refined white sugar. That's what the stage is. So that's another evidence of how these industries can influence the way the science is being viewed. Now it's going to change now. I think in 2000 something, one of the bills just passed. Now the sugar section also has to say how much is refined sugar, simple sugar, and all that. But this is another reason that you have to check the funding, right? Because the funding, sometimes intentional, but sometimes unintentional, can influence the interpretation of the paper. This is another one, vitamin D. Has anybody read this article in the New York Times? There's many other articles other than this, but there was this one person, well, a couple of people, but here they emphasize on Dr. Michael Holick at Boston University, who was one of the people who steered the vitamin D industry. And that's a big, big industry. It's $1 billion industry just for one vitamin D. And he is a vitamin D fanatic. So he really believes vitamin D is the most important thing on this planet. He even, in his book, even went on to say that dinosaurs died because they didn't get enough sunlight, and therefore they were vitamin D deficient, and therefore their bones were brittle. This person is clearly focused on vitamin D for academic purposes too, but he was also involved in the encouraging of vitamin D as a good thing or a bad thing. So I talk about this. Did I talk about vitamin D in the lecture once? All right, so it's one of the vitamins where the entire population is going through deficiency. There's a pandemic, and so the question is, and it's kind of in this article too, the question always was, the lingering question was, how is the general public deficient when the average value should have been averaged from the public, right? So if you get a number that's an average of this class, and then I tell you you're all deficient, then the calculation is wrong, right? But then that kind of mentality builds in. So it's not just that one paper. Whoever reads that paper and cites that paper, it can have a ripple effect. And then soon you have a field that agrees on vitamin D as something that everybody is most likely deficient in. And that becomes a problem, right? So you have to understand who's paying and who's doing the research. Okay, so I think this is one of the last ones. Like I said, the impact factor is calculated by the number of citations, total number of articles. It takes about 2 years. So in the third year, you'll see an impact factor. So the new journals won't have it, but this is basically what it is. So you should definitely reference it, but not based on it solely, right? So this can go a little skewed because it's a very clear metrics used by a lot of people. So a lot of universities use this metrics for promotion. Students will be judged based on the journals that they publish in by impact factor. It's not the best way, but it is definitely a culture that has persisted for a long time and is still true. So impact factor does not equal quality, but there is a loose connection there. You can definitely say an impact factor of 30, which is considered very high, paper would be okay, versus impact factor of 1, which is basically non-existent impact factor, you would be skeptical. So it kind of gives you an idea of what the journal, what kind of science the journal carries. Does not tell the quality of that individual article per se. Okay? So it's not that simple. So what does impact mean then? Why are we so focused on impact? This is another joke. If your impact factor is above 10, then you can enter. If it's lower, well, you know, it's a joke, but it's sad because it's kind of true. So what impact means, let's go back to Newton. Newton found or observed an apple fall from the tree. And then his conclusion after a lot of mathematical derivatives is that gravity exists. So he's the first person who ever figured out gravity by looking at an apple, but he figured out gravity. So that applies to pretty much everything, right? Because gravity is something universal. That's high impact paper. And then you have, you know, somebody else who was sitting in a tree and said, oh, orange also falls from the tree, right? So that's just like an apple. Oranges also fall, and therefore is subject to gravity. That's low impact paper, right? Because he already defined the general theories of gravity. Somebody else just made another additional observation that adds to it, which was pretty much predicted based on Newton's discovery. So this is what we mean. You don't want to base on papers that just do something to publish something, because they have to publish as part of their job, but some real discoveries, some real observations and original discoveries and interpretations. That's what we call high impact. All right, so these are some examples of papers that are widely read and cited based on impact factor and median citation per year. So obviously Nature is up there. It's a general thing. So these citations, you have to understand that although you are interested in a certain topic like aging, these general journals like Nature, Cell, and Lancet in Science don't just cover aging. They cover black holes. They cover climate change and all that. So those citations are going to be high because it's a public interest topic. So therefore, the calculation is not really equal compared to journals that cover aging, just aging, right? Because the citation numbers will be different. So you have to keep that in mind. But then these are considered very good venues for major impact journals because they're also read by everybody for that reason, right? Everybody reads it. And therefore, your study, which would have been only known to people in the aging field or interested in aging, can now be read by people who are interested in, I don't know, paleontology or something else, right? And strike new understandings of biology. So this is kind of like the list of journals. Not all are in here, but this is something that people talk about a lot. You get a lot of lists of these journal rankings and qualities. Okay. So I think this search engine, and then that's it. So how do you search for these papers? What do you guys use when you look for papers? When you go to the computer and say, okay, I want to find papers on aging and sleep. Yes?
I start with Google Scholar as
Yes.
opposed to Google.
Yes. So that's what I do too. Google and Google Scholar. If you go to Google, there's a section called Google Scholar that will just look for papers and patents. So that's a good way to look for it. And there are different filters that are less complicated than PubMed and more diverse. It's Google. So that's something to. So preprint is something new. How many people heard of preprint? We talked about open access. Now there's preprint, which is also free. Preprint is it's a complicated thing. Long story short, people can submit their paper to a preprint journal, and for biology, it's called bioRxiv. It's handled by Cold Spring Harbor, and it's post-publication peer-reviewed, meaning they upload everything that looks okay scientifically, and then whoever reads it can comment on it. And that does not now preclude publication in other journals. Like Nature will still publish your paper that you have uploaded to a preprint journal. So sometimes you will look for papers and it'll say preprint, bioRxiv. And the question is, can I cite this or not? And the answer is, you pretty much, you can cite it, but it's not currently peer reviewed per se, but it's just out there. So the policies probably differ per journal. In my opinion, I don't really care about preprint being cited as long as the studies are done rigorously and well. But it's really hard to gauge the quality of that particular field if you're not an expert in the field as a preprint, because it's not peer reviewed by experts. Okay, so that's the caveat. But it gets the information out to the public. Okay, so Google Scholar, definitely a place to start. I start from here, but there's also something called PubMed, and this is a website, a service from the U.S. National Library of Medicine. So it's government supported, and it's pretty much one of the largest journal databases for biological and medical sciences and related sciences. So that's one of the biggest ones that have been used until Google really kicked into that business. But again, don't forget, Google has their own algorithm, so it'll be skewed too. So PubMed and Google, to be honest, these are two of the ones that I use the most. And then I have subscriptions to individual journals that send me new papers based on my interest. And then there's other things like Scopus and Web of Science. And different fields use that a lot too. But at least in our field, we don't use Scopus as much. But some other social science I heard use that a lot. Web of Science is obviously a very big one. This is maintained by Thomas Reuter, and they are the ones that used to calculate, or I think they still do, impact factor. Because they collect all the citations, and it's a very complicated calculation and data collection. It has to be done by a big institution. And so Web of Science is also something else. And then there are new ones like Mendeley and all that, and there's other ones that USC now pays for, which I cannot remember. Dimensions, I think, is something else. It's a paid, is it, has anybody used Dimensions? I just learned about it last week too. Apparently USC has subscription, so you can get it for free. There are all these algorithms. So algorithm is key for search engines, right? And so different algorithms come up with different aspects of the search criteria. So they're all useful, but Google and PubMed are pretty much the two very widely used ones. Okay, so this is kind of what a paper looks like. It starts with an abstract, and that's where they get your attention. And then it starts with an introduction, a connection to what's going to come. There's some background information of where you're coming from. And then they talk about materials and methods, how we tested this, what are the tools that we use to test this, and then the actual results. These are where all the experimental data come out, and then they do a discussion, which it could be brief or long. Sometimes there's a conclusion. And then nowadays there's demand for a lot of data, so a lot of journals have what's called supplementary materials, which are a lot of data, like you were saying, there's a big volume that doesn't fit into that small, tiny space in the journal, but you can access it online and you can upload a lot of data there. And then disclosures, very, very important, and acknowledgements. So I am a shareholder of what, or I get paid by this company, or I have financial interest in whatever, that's all here. And then acknowledgement is thanks for the sugar industry for funding the paper or the research is here. And then the references. So these are some of the things you want to practice running through really quickly before you decide to read the paper. And also use it to write your own paper. Okay, so the last one is referencing. Woof, that was an hour. When possible, and make all efforts, reference articles that are within 3 years of age. So Richard said 1 or 2, that's very strict. I was having dinner with somebody in Boston, a well-known figure, and I was saying, well, that was shown like 3 years ago, when he suddenly said, that's so long, that's such a long time ago. So the standards are, new information comes out, it just spills out these days, and 3 years ago is not the same 3 years when we were talking in 1985. 3 years ago today would mean 3 million papers ago. So, in a sense. But there are landmark papers. If you have to cite a paper from the 90s or early 2000s, where it's a hallmark, landmark discovery paper, like the discovery of DNA. Okay, that's the discovery of DNA. You have to cite the paper. Then you can't. But generally, you want to keep within the last 3 years. Always cite the original study, not a secondary article like reviews. You can start off by describing the field with reviews, but when you come down to specifics, you want to cite articles and not cite other people's opinions or interpretations of the data. Right? You don't want to be a parrot. And when possible, provide a balanced view on controversial topics like vitamin D or effect of sugar on coronary heart disease. These things you want to be able to tell the people that you understand, but also provide them a view where yours is not also entirely skewed. Okay, so it's not that easy to write a paper, right? There's a lot going in. And I assume, like every year, I'll get a lot of emails by the time that you start writing the papers about, well, what do I say? How do I do this and all that? So we'll talk more individually then. So ask questions when you have questions. I'll also talk more about the formatting of the paper, and specifics regarding hypotheses. You want to have a hypothesis statement sentence where you clearly outline what your message is instead of burying it in the paper and leaving it to the reader to figure it out. You want to have a very clear hypothesis statement and then build a paper from there. Okay, let's take a break now. In 10 minutes, we'll be back.
10月6号，就下周。
那个是 midterm，
就下周。我去了，有一天我。
反正他会给播到一周的样子。10月9号，
在家吗？那就跟我一样的情况。
是不是有一个那个 final essay？
啊？人家还是人头。人头不够。
你刚刚喊我干啥？最后一个题什么意思？我还没写呢。
我这节课写了2道题。
你用的是什么研究方法？是不是那个 convenience？为什么要分层啊？
因为我们是研究不同的教育这样水平，然后就分不同的组。
不是啊，我们那个
选2个对比，我对比的是简单随机抽样的。
第二个题是我们选
啊？
这个方法。
你懂我
选2个。
第一个题是选2个对比，第二个题是那2个对比的2个水平的给我们的，所以我
没签吗？
对比简单随机抽样分层随机抽样，然后选是全先走一抽样。
你现在就走。
那我就选简单。
你现在走。
为什么？我们2个一组啊。
是要这样。
就是我们选的是一样的，但是我们解释的不一样。这不是我们的。
我们为什么选这个分层抽样？就是因为我们研究的东西它是不同层次的那个 education 的那个 level。
对。
然后还有什么原因？就这个原因，就写了这个。
那还能有啥原因？
我总觉得太少了。我在想，我上次分扣了我0.25，是不是因为我写的太少了？
但是我前面的那个对比，他写的比我还少。
真的。
就我觉得他就乱给分。
那对比我就跟你选不一样的。对比我跟你选不一样。
那你如果对比的不一样，你最后选的那个也得不一样。他没说，就是第一个题是要对比吗？你选2、3个对比可以给他。就是说你选2个对比是可以选3个。
哎，等一下，
你选2个。
第一道题不能选2个对比，然后他们有什么不同？然后还要从什么错误的方面？
哦，对，那个题我不会。
是啥意思？
他那个是为什么？这不是那些不同吗？为什么会造成这样的不同？
会造成不同的不知道，知道了应该，因为我记得那个就是 convenient sampling 是因为它不能代表这个 population 的整体，然后那个但是分层我不知道它的什么，还有一个我知道的问题就是那个 propulsive sampling， 它的问题就是。因为他们选的那些人都是因为有一些有 position， 所以他们也是是一些比较现成的。对吧？是的，这个
就是第一问是问你不是要选2个做对比？
对啊。
然后这2个做对比是对比它的什么相同不同啊，什么这些点。然后你对比完了之后，就这两个它会就是2种不同的方法，它会造成不同，就2种不同的抽样方法，最终得出的数据结果是不完全相同的。我们上课的时候不是试了吗？有的时候就测对比，有的时候测全部，得出来的数据不一样。
然后要分析为什么
造成的结果不一样。
好烦呀，不生气了。
我觉得造成不一样的就是就针对我们的来说的话，因为简单随机抽样，
就有读那个贝尔层，但是如果做分层出样，我们测100个低水平的，测100个高水平，这就分开了，所以它得出来的数据就会。那我不写那个你的那个sample，我写分层和。
就对比另外一个呗，分层和 cluster，比如说那个子群出样，或者四什么玩意儿，
我写那个出样，
反正就只确保对比的里面包含一个咱们的出样。
就一定要分析你自己的出样是吗？
对啊，你得分析完你才能写呀。就对比另外一个和这个，然后确定我们选这个更合适。比如说明天我们有3作业，抽4个是吗？抽5。
哎，我们这个下周就开始考试对吧？不是说下周才考吗
？Any topics you guys want to talk about? The term paper?
9号吧，不是说9号。我听到他们说9号。
Yeah.
Oh, I thought they were like question based or something.
I have a list from last year, but I want to tailor it every year. CRISPR could be another one, which wasn't a big deal 2 years ago. Now it's like the thing.
Well, it was like a big deal in theory, and now it's like.
Yes, I have to change my slides next year. Don't worry, it's not gonna happen. No, now panic.
Yeah. I mean, like Monsanto is pretty scary because when they first started talking about possibly using it for vegetables, I was like, I don't want to think that I'm eating like alien
I
vegetables.
compare that to Monsanto every day. That's the danger with germline. It goes in and it doesn't come out. And then the question is, who has the right to the genes? Intellectual property-wise, legally, but also which insurance company will cover problems arising from that gene combination. Like, I didn't choose to be born with it, somebody put it in there. Well, maybe we should sue that guy for all my health insurance bills. Yeah, and it's a good way to take over a whole population. Right? That's exactly what Monsanto did.
Yeah.
They bought out, they dried out their neighboring farms by suing them, financially draining them. Because the bees will go and pollinate, and then they go around sampling stuff from the neighboring farms. Oh, you have our gene, you stole our gene. Now you gotta pay for this. And that's how they drove everybody out of the field. Yeah.
可以选择一个明显跟你这个
Same thing for you.
搭不着边的一个东西，然后狠狠的把它喷一顿就行。Okay, so like the term papers are that broad, it's like Alzheimer's. It's only like 7 pages, right?
Yeah, I mean, we can talk about Alzheimer's is a broad thing.
Yeah.
There are many things to talk about.
Okay.
I mean, I don't want to give people too specific of a topic, then it might not be of their interest, but I want to give them certain categories where you can identify your interest.
When will we be assigned? When will we be assigned this? The topics.
Topics, so last year, for example, we had menopause.
No, like when, sorry.
Oh, when? It's in the syllabus. Towards the second half of the last year. We had, one that was popular was Asian sex. A lot of people were about that. It's a serious problem, which we don't talk about because it's hush hush. Okay. All right, let's get back to class. So I was just saying, for the term paper topics, I haven't decided completely. So if you have some interesting topics you would like to write about, please email me. And if it fits a more general interest, I can put that on as one of the lists. Okay, so now let's talk about some physiology. Away with the whole paper citation and journals and all that. Where am I? Okay, so the skeletal muscular system. One has to do with the skeleton, the other has to do with the muscle, obviously, but they're combined together because they work together. So in most physiology classes, you'll see these two systems combined. Right, so the skeletal system, we'll talk about the bones, obviously, but also cartilage and joints, which are all big topics in aging. And the muscular system, obviously, muscles, but mostly skeletal muscles. How many bones do we have? 220? 200, I'm getting different numbers now. 236. So we have 206 skeletons on average. My friend had 208 because he had an extra vertebrae, which explained why he couldn't bend during PE. But most people have 206, plus minus 1, depending on how you look at some bones. But general consensus is 206 bones. That's a lot of bones. That's a lot of parts of the body. So we can divide the bones into axial skeleton, which is up here. So there's 80 bones here: the skull, the rib cage, your spine, your vertebrae, and all the bones in your face are compose the axial skeleton. And the appendicular skeleton, there's 126. This is doing this again. I have to, sorry. Okay, so here. So these are the periphery skeleton, the appendicular skeletons. Okay, so we can divide it largely into two parts based on location. Funny thing is, most things here you can break and survive. Most things there you break and it could be non-trivial. So some of the functions of the bone, right? So we can understand what changes with age and how that can impact our lives. So obviously the skeletal system provides the point of attachment for muscles and therefore is important for movement, right? You can't move if you have no bones. There's a scene from Harry Potter where there's a magic thing that makes bone disappear, and the result is you can't move, right? The most obvious result. What else does the bone do? Helps us move. Protection, support, but also protection later on. You know what? Just go on. Yes, bone marrow. So it supports us, gives you a frame for things to attach, like your heart and your intestines, everything to be structured. Gives you support and it gives you protection. Your skull protects your brain, your ribs protect the lungs, and so forth. And like you just said, the marrow, so the tissues inside the bone makes blood. So your blood is generated from your bone. Excuse me. Both red and white blood cells. And that's because your hematopoietic stem cells, which give rise to all your blood cell types, are formed in the bone marrow. So we'll talk about that too. And the changes that happen there, which will link to our immunity lecture. And it's a storage place. It stores minerals like calcium and phosphorus for the body to use, and it also stores fat for energy. So it's not just a stick that gives you support. It's an actual living, breathing tissue that has a lot of different functions. So some of the classifications, I'm not going to go into detail here, but these are just saying that there are different types of bones, and you can classify it based on shape, right? The long bone, the flat bone, the irregular ones like your vertebrae, there's the short bones, and the sesamoid bones. Which form follows function, and different biological processes happen in different types of bone. For instance, the long bone will have a lot of marrow that will be part of your hematopoiesis. Okay, so this is what a long bone looks like if you cut it open. Okay, so there's the top part, which is the proximal epiphysis, but we're not going to talk about the anatomy. Just wanted to say here that the bone is not just dead material that builds up, not dead calcium and nothing else. It's actually a very, very diverse area of cells that live there and metabolize in a mesh of calcium-based structure. So it's not solid, it's spongy inside in the proximal area. And there are a lot of blood vessels that go in. If you go in the middle, in the diaphysis, in the middle, the long section, if you cut that open, you will see marrow. So this is the spongy red marrow, which makes your red blood cells and your immune cells. And the yellow marrow is basically fat. And so, how many people actually had bone marrow in restaurants? It's a delicacy now, right? They bring it out as if like this is the thing. But in fact, historians tell us that cavemen, our ancestors, one of their sources of energy was marrow. So you go around and you see a dead animal, crack the bone, get the marrow, and that's about 300 calories to 400 calories. Nothing, not bad. So, you know, it's a food source. It's energy that's stored there. Okay? Any questions here? No? It is pretty delicious, though, if you put it on toast. Okay, so the structure and microscopic anatomy. Like I said, there are cells. Okay, so there are substructures within the bone, which I'm not going to go into detail, like osteons. They're circular structures, but the main message here is that in between these structures, there are these cells called osteocytes, which perform deposits calcium or cleans up the calcium. So we'll talk about that a little bit more later. So there are a lot of cells there, and like I said, this is the top part. The hematopoietic stem cells are there too in your marrow. So that's where a lot of your immune cells and your red blood cells will be made. So your bone is full of a lot of different types of cells. Okay. Let's see. What do I want to emphasize here? I do want to talk about the osteoclast and the osteoblasts more in detail because there's the direct connection to menopause here. One of the problems that happen upon menopause is loss of bone density. And these two guys are considered the culprits and are targeted for drugs to fight that menopause-induced bone loss. So this is just a video to show the
structure of bone.
Yes.
Objective.
Yes.
To learn the basic structure of bone. As part of the skeleton of vertebrates, bones offer support and protection to various organs of the body. In addition, they have the ability to produce blood cells and store minerals.
And energy.
A bone has an elongated, hollow central body, referred to as diaphysis, and two terminal parts known as epiphysis. All bones are surrounded by a tough layer of connective tissue, known as periosteum. It is through this tissue that blood vessels pass, carrying oxygen and nutrients to the bone. Inside this periosteum is a thick layer of cortical bone, commonly referred to as compact bone. This outer shell of the bone is dense, strong, and resistant to bending. Because of these characteristics, it makes up about 80% of the skeleton. This dense layer is filled with organic ground substance and inorganic salts. In between these substances are very tiny spaces that contain the bone cells known as osteocytes. As compact bone matures, it develops a network of interconnecting vascular canals, referred to as Haversian canals, which contain blood vessels that supply nutrients to osteocytes. The compact bone will surround the Haversian canals in layers known as osteons. Inside the compact bone is the cancellous bone, commonly referred to as spongy bone or trabecular bone. This layer is filled with numerous large spaces, giving it a spongy or honeycomb-like appearance. The porous nature of the spongy bone does not add mass to the overall structure, but still provides greater strength and rigidity. Inside the bones can be found a soft, spongy tissue known as bone marrow. There are two types of bone marrow, red and yellow. Red marrow, which consists largely of hematopoietic tissue, is responsible for the production of red and white blood cells as well as platelets. Yellow marrow consists largely of fat cells and produces some white blood cells. Summary: bone is an organ composed of dense connective tissue. Bones are covered by periosteum, while its two main layers are compact bone and spongy bone. The hollow portion of the long bones is filled with marrow. Red marrow produces blood cells. Yellow marrow produces some white cells.
Okay, so that's the basics of it. One more. So this video I'm going to show later on when we talk about menopause. I don't want to go into the details of the anatomy too much. I just want you to focus on
the human skeleton
relevant
gives the body its
parts
shape
that
and
have to do
provides
with
physical
cells.
support for the systems contained within. It also forms part of the musculoskeletal system that enables us to move.
Support, protection,
The structure of bone is optimized so that it is strong
blood
but
cells,
relatively lightweight.
energy storage. These
The
all
interior
change
of
with
bone
age.
is
That's why we
composed
have
of bone marrow.
categories.
It is surrounded by two major types of bone tissue: cortical bone, or the hard outer shell of bone, and trabecular bone, the spongy-looking center. The amount of each type of tissue in bone is dependent on the function of that bone.
Amgen always has
The basic unit of cortical or compact bone is the osteon. It is composed of successive concentric lamellae. This structure contributes to bone strength by resisting bending. Cells called osteocytes are distributed within the concentric lamellae.
So here are the bone cells.
Osteocytes form a complex network that is thought to be important in maintaining the viability and structural integrity of bone. At the center of the osteon is the Haversian canal. These canals contain blood vessels and nerves. The blood vessels within bone facilitate the exchange between osteocytes and the blood. Trabecular bone is present in the interior of some bones and resists compression. Osteocytes are also contained within its structure and again play an important role in sensing local changes in strain. Trabeculae are covered in a layer of flattened lining cells that are thought to be involved in the dynamic process by which bone is formed and broken down. Bone marrow is found within the interior of bones. The surrounding trabeculae and vascular network provide structural support, nutrition, and a waste removal system for the heterogeneous group of cells found within this space. Bone marrow is a site for hematopoiesis, the process by which the cellular components of blood are formed.
Okay, so I think the second part of the video talks about bone formation, which we'll go through. So the bone has bone marrow and osteocytes. The bone marrow has the hematopoietic stem cells. So if you do bone marrow transplant, so if you, for instance, in the case of leukemia, what you're actually doing with radiotherapy before you introduce the healthy hematopoietic stem cells is killing all your hematopoietic stem cells in the bone by radiation. So that's where the problem starts. You can also flush it out. You can ask that to Ryan. He does that a lot, flushing out bone marrow from animals to collect immune cells. But let's go from the beginning. Actually, you know what? I changed the order of the lecture. We'll get back to the cell types and later on when we talk more about aging. But let's go through the other categories of bone or the skeletal structure. Okay, so that was the skeletal bones, and then cartilage. There's 3 major types: the hyaline cartilage, the elastic cartilage, and the fibrocartilage. The hyaline cartilage is the most common. So we're talking about stuff in your nose here. That's not really skeleton bone, but it's cartilage. Your ears, they're tough but flexible. They're basically closely packed collagen fibers. They also connect parts of your body, ribs to the sternum, and supports respiratory tract functions. And the other also covers where the bones meet. Elastic cartilage is, sorry, the flap of the ear is elastic cartilage. The epiglottis we talked about in the digestive lecture, the thing that comes up and down and closes the trachea, that's also cartilage. Okay, and then the fibrocartilage, we're not going to talk about much here, but basically very, very tough, lots of collagen. It's found in the spinal column between pubic bones and pelvis. It's very resistant to compression until it breaks. And that's the end of the story. So where can we find them? Again here, what we call the disc is basically fibrocartilage. How many people have or know people who have disc problems? That's basically your cartilage slipping out of the location. So that's that kind of cartilage. Elastic cartilage and hyaline cartilage. Okay. Let's see. Yes. Why did I not talk about articular cartilage? Oh, it's part of the hyaline cartilage. Yeah. So we're going to talk more about the articular cartilage. Why did I put that on the side? So articular cartilage is a type of hyaline cartilage that's specifically between the areas where bones meet. So joints, basically. Okay. This is a video of cartilage.
Cartilage is this fantastic tissue that makes up that flexible part of your ear, the end of your nose, and the cushioning between your joints. It's also what the skeleton of animals like sharks and rays are made up of. If you're an athlete, understanding the basics of cartilage will help you prolong your career. Here's what you need to know. First, cartilage is a connective tissue like muscles and bones, yet they're also very different. If you break a bone or tear a muscle, you know it right away, because it's full of nerves. Cartilage, though, doesn't have nerves, so you won't know you damaged your cartilage unless it affects the underlying bone. Also, those bones and muscles will heal. Cartilage, not so well. But to get why, we first need to distinguish between a few different types of cartilage. There's elastic cartilage, which is very flexible and found in places like your ear. Then there's hyaline cartilage that is super smooth and tough. It has minimal flexibility, but its glassy smooth surfaces keep our joints sliding smoothly. Then there's fibrocartilage. This cartilage is tough and flexible, but not particularly smooth. It's found in places like your menisci and the intervertebral discs. Many people have this idea that cartilage doesn't ever heal or grow back. In truth, it can, but very, very slowly. Like other tissues, cartilage is made up of cells. These are known as chondrocytes. Now, when other tissues get damaged, they are able to essentially migrate to the wound and divide and multiply rapidly. Chondrocytes can't do that easily for 2 reasons. First, they're found in a thick matrix, so it's hard for them to migrate to new areas. Secondly, there are no arteries or veins in the cartilage, meaning there's no blood supply to help feed and nourish the multiplying cells. The limited supply they get through diffusion just isn't enough for the rapid growth that is needed. Let's take this example. So say you suffered a joint injury, like ruptured ligaments, menisci, etc. This destabilizes the joint, which in turn affects the cartilage in the long term by wear and tear. This process can take a year or a decade after injury, but it's not reversible. The early changes in cartilage are hard to feel since there are no nerves. But after losing most of the cartilage, the two highly innervated bones are exposed and begin to rub against each other. Yeah, and that really hurts. At this point, the doctor can only medicate the pain since most of the cartilage is gone. If detected early, sometimes doctors will try to encourage cartilage to grow back in the area by putting a bunch of holes in the underlying bone that penetrate the bone marrow. And they call this microfracture. This essentially provides a blood supply and allows some stem cells in the bone marrow to migrate to the injured area to regrow some cartilage. The problem is that it's not that nice, smooth hyaline cartilage that we want. It's essentially scar tissue-like fibrocartilage. It does help protect the bone, but it's not as smooth as we'd all like, and thus doesn't work as well. Since the goal is that nice, smooth cartilage, doctors have a few other advanced cartilage repair techniques. Often they'll take grafts from elsewhere, either your own cartilage or from a cadaver. But you can't just take the cartilage. You take a plug that consists of the cartilage and the bone. The implanted bone will heal quickly with your bone and hopefully lead to a successful operation. The problem with this is that your body may reject the tissue coming from another patient, or if you take the cartilage from another part of your joint, then you leave a new hole in your joint. For future repairs, scientists are working on growing these plugs from our own cells. For instance, one technique could be to take adult stem cells from your own fat cells that can turn into bone and cartilage. Then, through different techniques, tell those cells to either turn into bone or cartilage, and then insert that whole thing back into the damaged area. So, if you're an active individual, here's the key. Be kind to your joints and cartilage. You only have so much, and while it does have some healing potential, it's not much. Also, if you injure your joint, go to a trained orthopedic doctor right away. It'll be a lot easier to salvage your cartilage if you detect the damage early than if you wait until it's mostly gone. Thanks for...
Okay, questions? All right, so let's go forward. One of the major problems with cartilage joints, basically, is arthritis. Age is the strongest risk factor for osteoarthritis. Sorry, I moved around the slides a little bit. Okay. So, risk factor for osteoarthritis. So there are different types of arthritis, which I thought I had in here. I'm sorry. Okay, so here I did talk about here. More than 50% of the cases occur after age of 65, so it's one of the rare cases where wear and tear is a big part of aging. It's the most common disease in the elderly, and it definitely limits your mobility and causes disability. So young, nice joint, and then older person's joint. So there's two types of arthritis that are generally discussed. One is osteoarthritis, which is what we just talked about, and the other one is called rheumatic arthritis, which is an autoimmune disease. So this is a different thing. It occurs much less frequently because this is a disease where your immune system is attacking your own joints. And so that's not an age-dependent disease, that's an autoimmune disease. So it can happen fairly early, about 30 years of age. Nobody really knows why, as is it's a common thing for autoimmune diseases. So osteoarthritis is a degenerative joint disease, right? It's caused by the breakdown of cartilage, the most common type. 75% of those reaching 75 years of age experience. That's a very high percentage. And there is sex disparity, more frequent in women. And again, cause is unclear. So what do people do with arthritis? In the video, we said you can't really do much when you lose your cartilage, other than surgery, which is still not very good. So what do people generally do then? Joint replacement, but before you get to that, in a more population-based approach. Drugs. Those are to reduce the local problems. But people take supplements, right? So based on what we just learned, this is just a rendering of that. Based on what we just heard, do we think, or do you think these supplements help with arthritis? Because this is a huge market too. Bottles and bottles everywhere, right? Yes.
My guess is this is more of the placebo effect, because people usually take aspirin or Advil and then they take a supplement, and so you can't tell which is really
Exactly.
helpful.
Right, right. Why do you think this will not help? Glucosamine and chondroitin. Let's go back to the question then, the actual substance. Glucosamine and chondroitin, what is it? These are glycoproteins, like hyaluronic acid, glucosaminoglycan subunits, which basically are proteins with carbohydrates sticking out that make things cushiony and soft. So why would this work or not work? Any ideas? What's the whole idea here when you take these supplements? And a lot of people take the supplements.
Well, wouldn't it have to infiltrate the damaged joint and serve like a putty and repair the natural surface so it's smooth?
Right.
But none of this makes any sense.
Right. Because you can't regenerate them. Right. So basically, you're giving them ingredients that people think make up part of the cartilage or important for cartilage. And the simple thinking that you take more of what composes it will go magically to that area and fill that area. And that's basically how they sell this. You have joint problems, is because you don't have enough of the stuff that should be in the joints, right? I had a friend when I was very young, whose grandfather, he had really bad vision, it's like poor sight, and his grandfather made him eat cow eyeballs because he thought that his vision problem was driven by the lack of components of the eye. So he made him eat cow eyeballs, which didn't work obviously, but it's the same kind of concept here, right? So, yes.
My dad actually took one of those and he said that it feels better, but it's a short-term thing. He stopped taking it already.
But we shouldn't take it for granted because based on our knowledge of how cartilage works, it should not work, right? But the same question with yogurt. We don't find those bacteria in our gut, but people always say it's beneficial, that you feel better, right? So is this really purely placebo, or is it something else other than going to the cartilage and reconstituting whatever was lost, right? Does anybody take glucosamine and chondroitin? My mother makes me buy bags of this from Costco. And I've tried to explain to her, it doesn't go, Mom. And that's why I don't have her read my papers. So, clinical trials, double-blinded, large-scale, multinational. So not just one country. There are a lot of studies published on the effects of glucosamine and chondroitin for knee osteoarthritis. And there are a lot of names. These clinical studies, one of the gifts or one of the abilities you have to have is to name your study in a very sexy way. So these guys called it a LEGS study. Something like long-term something, I can't remember. So this is a huge clinical study. And the objective was to determine if dietary supplements of glucosamine and chondroitin result in reduced joint space narrowing. Basically, does it fill what's lost? And pain among people with symptomatic knee osteoarthritis. Methods, double-blind, randomized, placebo-controlled clinical trial with 2-year follow-up. So double-blind, randomized meaning people who get it don't know, people who assess them don't know, so nobody's biased. People take it are not biased, people measuring are not biased, and is randomized, meaning you get a cohort of people and randomly distribute them to control and the drug group. And so it's placebo-controlled because it's not like one group takes a pill and the other group doesn't take anything. They take the same physical pill. One has the ingredients, one doesn't. So it's a placebo control. So pretty much what everybody can think of as a control. And they follow it for 2 years, right? 605 participants, which is a very large study. And the age group ranges from 45 to 75. So the middle age where you start having these issues, and 75 where about 75% of the population experience this problem. Reporting chronic knee pain and with evidence of medical tibiofemoral compartment narrowing, but just basically saying they made sure that there was a problem in the joint from the beginning. And these were the criteria. Once daily glucosamine sulfate, 1.5 grams, and then chondroitin sulfate, 800 milligrams, or both, or matching placebo capsules. Okay? And this is how they do it. Over 2 years, digitized knee radiographs, so actual visual confirmation of the space between the two bones. Maximum knee pain was self-reported in a participant diary for 7 days every 2 months over a year. Pretty rigorous, I would say, well designed. What do you think the conclusion was? I see some smiling faces. You know what's coming. None of the treatment allocation groups demonstrated significant symptomatic benefit above placebo. So you can find all the data there in the clinical trial government website. That was one study. This is an example of another one. Here they named it GATE. That's another clever title. Again, OA, osteoarthritis, functional limitations, older adults. Methods, again, a 2-year, again, double-blinded placebo-controlled study at 9 different sites in the U.S. ancillary to this trial. Enrolled 662 patients with knee osteoarthritis, yada, yada, yada. This is the criteria. Here it was glucosamine 500 milligrams 3 times daily. The other one was the same amount, but once daily. Chondroitin sulfate 400 milligrams 3 times daily, so it's a little bit more than the other study. The other one was 800 1 day. Here is 400 3 times, and a combination of both. 24 months. Conclusion: over 2 years, no treatment achieved a clinically important difference in whatever pain index or function as compared to placebo. So, yes?
Is clinically important supposed to, how does that differ from significant?
So you can have statistical significance, which is something that's quantifiable and calculated. You can calculate it. Clinical significance becomes a little bit more subjective because it's more to do with the health of the person. In this case, when they say clinical benefits, they're referring to the criteria that they set out, right? So there's defined categories and degrees of separation between the bones where they diagnose accordingly. But none of them, basically what it means is that none of the treatments reduce the space between the knees, nor reduce the pain significantly. So there's statistical significance and there's clinical significance in that sense. So the answer is, so far the evidence is against these supplements having any benefits, and there was benefit of the doubt. We know that it probably won't go to the joints, but maybe there is something. But turns out that doesn't seem to be the case. Okay. So that's joints for you. Let's move on to bone homeostasis. Let's see. How does the bone retain itself? How many times do you think when your bone is made, you live with that until you die? Or do you think you regenerate your entire skeleton throughout your life? And how many times if you do so? How many people think bone is bone and we keep it as we go? And we regenerate a little bit as needed? How many people think bone gets turned over periodically, and so throughout your lifetime you will completely turn over your entire skeletal bone structure? The answer is, an estimation is most people will, I think the number was 2.2 times. You'll turn over your entire skeleton about twice, because bone is not a static organ. It's a continuously remodeled tissue. So homeostasis is important, which means there's constant breakdown of seemingly perfectly fine bone. Your body will resorb it and then rebuild it. So it's constant building and resorption. And these are done by two different types of osteocytes, bone cells. Osteoclasts, whose role is bone resorption, come and nibble away your calcium. And these are basically a different form of your immune cells known as macrophages, which we'll learn in the immune lecture. Specialized macrophages that eat part of your body away. And then there are osteoblasts, which form your bone. So minerals and collagen deposits are done by osteoblasts. So it's a balance between osteoclasts and osteoblasts that allow your bones to be healthy. Okay. Oh, here you go. Is this an Amgen video? Yes, the music will come. So bone remodeling and modeling.
The skeleton changes across the human lifespan. This is characterized predominantly by bone formation and growth throughout childhood, followed by a gradual loss of bone density that begins in early adulthood that can accelerate significantly in older adults. The density of bone is modulated by a group of cells including osteoclasts, which are multinucleated cells that resorb bone, and osteoblasts, which refill the resorption cavities created by osteoclasts. Osteoclasts anchor themselves to the surface of bone. This creates a microenvironment underneath the cell, which is referred to as the sealed zone. Within this zone, the osteoclasts create an acidic environment that dissolves the bone's mineral content. Once the mineral content of the bone has been dissolved, enzymes released from osteoclasts remove the remaining collagenous bone matrix to complete the process of resorption. Following resorption, osteoblasts move into the resorption space and start to produce and deposit organic matrix called osteoid. Osteoid, a substance made predominantly of collagen, forms a scaffold in which minerals including calcium and phosphate begin to crystallize. Some active osteoblasts become trapped within the matrix they secrete and thereby become osteocytes. Other osteoblasts will undergo apoptosis or will revert back to lining cells which cover the surface of bone. This cycle of bone resorption and formation is referred to as remodeling. There is also a process where bone formation by osteoblasts occur without prior bone resorption by osteoclasts. This results in an increase in bone mass and is referred to as bone modeling. Bone modeling promotes the growth of bones and is important for maintaining bone strength. Remodeling also plays an important role during bone growth by optimizing the growing structure. After the age of 30, most people experience a gradual loss in bone mass due to a relative decrease in the activity of osteoblasts compared with osteoclasts. However, there are many factors that impact the process of bone remodeling and influence the degree of bone loss we experience as we age. For example, medications such as glucocorticoids, which can promote osteoclast activity and also reduce bone formation. Proper nutrition and physical activity can help strengthen bone. It is also believed that osteocytes form a complex network in bone that can sense any increased workload on the bone and respond by triggering the differentiation and activity of osteoblasts to increase bone density.
This is an important point.
Conversely, when bone experiences reduced loading conditions, such as during long-term bed rest, resorption and remodeling increase to eliminate underloaded bone. Loss of bone mass reduces its strength and increases the risk of fracture. This highlights the importance of staying active, maintaining good nutrition throughout life, and being aware of personal risk factors associated with low bone density.
Okay. So, let's see. Bone mass goes down with age. And there's a significant drop here because of menopause. The males tend to have higher bone density or mass initially, and they taper off as well. Starting at age of mid-20s, I would say, you would start to experience some changes, definitely by your mid-30s. So we're all done with the stage of building muscle mass, bone mass. We're now in the stage, and welcome to the stage of loss of bone mass. And that's because, well, not only because, but largely because the osteoblast function declines with age. Let's see, okay. So what is the only way that is known to increase bone density? Weight training, gravity. So we saw in the video, osteocytes sense the workload, right? So that's another reason that you should not only focus on aerobic exercise, but weight training is also very, very important. And then we'll talk about why it's important for the muscular structure too. If you're a bodybuilder, anybody used to be a bodybuilder or weightlifter? You used to be a weightlifter? No. The bone thickness increases if you are a competitive weightlifter. You should check out if your bone density went down. And it's pretty clear. So for instance, when there was an excavation for, I think it was one of the King Henry, I can't remember which one, but obviously he was a very well known weightlifter. He was very proud of his weightlifting abilities. And it was funny because one of the criteria that was validating his skeleton was that the fact that this was a skeleton of a weightlifter, because you can see the broadened and super thick bones. So as you get older, there really is no way other than applying more gravity to your bone to maintain bone density. So if you lose your bone density to a certain level, it becomes a disease. And that's known as osteoporosis. And some people consider it a usual course of aging, but in fact, some people, including myself, consider this a disease of aging. Clearly, there's more people and more females because of menopause. So this is a disease that occurs when bone remodeling declines, right? Now, what are some of the immediate problems with bone density loss and osteoporosis that you can think of with age?
More likely to break a bone.
Yes, and why is that a problem?
Why is that a problem?
Mm-hmm.
If you break a bone?
Mm-hmm. What would that lead to?
Decline in general.
You can't move.
You can't move.
Which starts a whole lot of, it opens the gates to disaster, right? Mm-hmm. If you're bedridden, it's a feed-forward disaster where now you're not moving, so your bone density goes even more down. And it's something that if you fall into, it's really hard to get out because of that reason. If there is a hip fracture, very, very big problem too. But then if you consider the fact that fall is a major event in the elderly for other reasons I'll talk about in the muscle part, your bones will break easier, right? So there's this whole integrated problem with bone mass loss in osteoporosis. Okay, we haven't even got to the immune part of this. So exercise promotes bone homeostasis, so there's no excuses. How many people lift weights regularly? Not competitive, but regular. How many people can lift their body weight? Oh, either you're really light or you're strong. How many people bench press? How many can bench press their weight? Oh, pretty good. How many people can do this? or this. That's pretty amazing if you think about it. I can do this. I used to be able to do this. I have not tried that. But exercise, exercise, exercise. That's one of the reasons too when it comes to exercise. Okay, so menopause is very, very strongly linked to bone homeostasis. The evidence is very clear. There's a dramatic decline, as we just saw. And again, the endpoint, the consequences are pretty significant. Fractures lead to pretty much all problems. And the reason for menopause is, as you expected, menopause leading to osteoporosis, as you expected. It has something to do with reduced hormones, estrogen. And estrogen has a very strong role in bone remodeling. So we'll see that a little bit later. And therefore, osteoporosis occurs more frequently in women. So this is a drug that I believe, the reason Amgen has all these videos is because they're pretty much the only company that has an FDA-approved drug for this. And it's still not, very good. Maybe some other company has another drug. I can't remember.
After the age of 30,
This
bone
video goes
resorption
into
will
a little
slightly
more
exceed
detail of the
formation,
molecular
and bone mass
pathways,
begins to diminish.
which I put there just
In
for
women, this can
reference.
become even more of an issue following the onset of the menopause, where declining estrogen levels further increase the rate of bone resorption. Osteoclasts are regulated by various signaling molecules, including rank ligand.
Cell surface markers?
Rank ligand promotes the differentiation, activation, and survival of osteoclasts via an interaction with its receptor, rank. Once activated, osteoclasts resorb bone. However, the hormone estrogen is thought to repress rank ligand signaling. Downregulation of rank ligand expression leads to decreased activation of rank and a subsequent decrease in osteoclast-mediated bone resorption. Estrogen has also been shown to stimulate the expression of osteoprotegerin, which inhibits the activity of rank ligand by preventing it from interacting with its receptor. Following the onset of menopause, estrogen levels start to decline. This can lead to increased rank ligand production, which is associated with increased bone resorption in postmenopausal women. Increased bone resorption after the menopause leads to the accelerated loss of bone mineral density, which can result in the more severe condition of postmenopausal osteoporosis, in which the skeleton becomes increasingly susceptible to fracture.
Ooh.
Vertebral collapse is often secondary to osteoporosis and is more prevalent in women. In osteoporosis, the thickness of both cortical and trabecular bone decreases over time, suggesting that both of these structures play a role in the development of vertebral fractures. These events, such as fragility fractures of the hip or vertebrae, may contribute to the painful and debilitating symptoms that can arise from osteoporosis. Several other factors influence the rate of bone mineral loss. These include genetic factors, lifestyle factors, and the use of certain medical therapies, all of which are thought to play a role in the development of osteoporosis.
So I think I'm going to stop here with the bone. But let me just make two, yes, question.
My wife is on these drugs to
Yeah?
prevent osteoporosis because she's in her early 70s. They have nasty side effects,
I can imagine.
and they prevent further decline, but they don't promote growth.
They don't promote.
And so the key is, how do we promote growth? Are we working on immunotherapy or stem cell therapy?
Yes, so that's the thing. Sadly, the answer is still exercise and weight training. It's the only way. The problem here is the same as with many age-related problems. We don't understand the molecular mechanism very well. So you can't target something that you don't understand. Here, they nailed it down to rank and rank ligand, but then that's part of the story. It's not the whole story, and it's a pretty ubiquitous system, so side effects are a big problem. I didn't put it here, but the loss of bone is not just for related to fracture, but also your support system. So I was trying to go back to all the main points of the bone, minus the bone marrow, because we'll talk about that in the immune system. So support, protection, and movement, right? One of the key aspects when you ask somebody to draw a very elderly person is a hunch posture, right? And that's because the bone loss in the vertebrae lose their ability to support you. So kyphosis in serious cases where you have a hunchback kind of situation. Also, some people you might have heard say, oh, people tend to shrink when they get older. That's another integrated combined loss of bone mass too, in general. It changes their structure. And then the cartilage, obviously. Okay, any questions on the skeletal part? Okay. So go and do your weight training. Don't wimp on your leg day or your back day or whatever you have. All right, so let's move on to the other part of the skeletal muscle lecture, the muscular system. Right? Our body is covered with muscles all over, and we're just talking about the skeletal muscle. Right? In the digestive lecture, we talked about smooth muscle, which has a different mode of operation. It's more of a squeezing action. Skeletal muscle is more of a contractile action. So if you had your digestive system based on a skeletal structure, muscle structure, your digestion would be something like this instead of a nice continuous squeeze. So very different, the same muscle but different form for different functions. Okay. Muscle cells are elongated. They're based on contraction, which is due to the movement of microfilaments. So we go back to our lecture 2 with actins and tubulins and all the filaments. Some terminology that you might want to keep in mind. Every time you hear a prefix myo refers to muscle, mis refers to muscle, sarco refers to muscle, flesh. So sarcopenia is a problem of loss of muscle. Sarcoma is a cancer that rises from this lineage of cells. Okay, muscles are responsible for all types of body movements. Every movement that you just made is because of your muscles, and it's based on simple contraction. Okay, so these are the machines of the body, if you will. We just said that. Skeletal, cardiac, smooth. So form follows function. Skeletal looks like this. Cardiac, a little bit different. And smooth muscles look like this. They're more of a twisting motion. And cardiac we'll learn more about in the cardiovascular lecture. Okay, so let's go to skeletal muscle. So most have to be attached to the bones by tendons. Cells are multinucleated, so I'll talk a little bit about that. How many of you were at the lecture when Young Jang was here about 2 weeks ago about muscle regeneration and stem cell therapy? Okay, were you there? No, nobody was there? Okay, that was a really interesting talk about regenerating muscles. Anyways, they're striated. You can see visible banding because of the structure. And they're voluntary. You can move it whenever you want, which is different from the other types of muscles, your cardiac and your intestinal muscles. Although, despite some people claiming that they have control over those muscles, it's not really evident. Let's see. It's surrounded by a lot of connective tissue, so it's very tough and strong, but it's very energy dependent, so it tires easily. And these are different components or parts of the muscle that I'm not going to go into. These are just anatomy of the muscles, which is not the point of this lecture. Let's see. So I'm going to skip on this too. sites of muscle attachment, bones and cartilages and connective tissues throughout the body. Okay. So the basic segment or the units can be considered sarcomeres. This is the actual machinery of your muscles when you break it down to the cellular level. So we go into the cells now and see how the muscles can do this, right? What's happening right now in my arm is the filaments, the thin and thick, so myosin, is basically, remember the motors I showed you where they move cargo? It's basically the same system. It's an energy-dependent movement that allows these the thin filaments to move along. So I think I have a video of this. No, so this is lecture 2. Again, we're talking about cytoskeleton that allows the movements of in the muscles. Yes, in this. It's the same system as this. It's basically a wire that supports the movement of other targets. In this case, your thin filaments. But the motor is the same. It's dynein-kinesin based, ATP based. It's energy dependent. Okay, so I think this has a bit more visual explanation. This is a little hard.
You use muscles every day to do activities. This woman is using muscles to breathe, circulate blood, and move her hand to take notes. Your cardiac and smooth muscle tissues are involuntary. You do not consciously control their actions. Skeletal muscle works under voluntary control. Skeletal muscles are composed of bundles of muscle fibers. Muscle fibers are long cylindrical cells containing several nuclei. Muscles will contract or relax when they receive signals from the nervous system. A neuromuscular junction is the site of the signal exchange. This is where the synaptic bulb of an axon terminal and muscle fiber connect. Muscle fibers are composed of many myofibrils. A myofibril contains contractile units called sarcomeres. Sarcomeres run adjacent to one another down the length of the myofibril. Each sarcomere consists of alternating thick and thin protein filaments, giving skeletal muscle its striated appearance. The muscle contracts when these filaments slide past each other. The thick filaments are myosin, which are anchored at the center of the sarcomere, called the M line. The thin filaments are composed of the protein actin, which are anchored to the Z lines on the outer edges of the sarcomere. Because the actin filaments are anchored to the Z lines, the sarcomere shortens from both sides when actin filaments slide along the myosin filaments.
Kicking the actin.
Although the action between the filaments is described as sliding, the myosin filament actually pulls the actin along its length. The cross bridges of the myosin filaments attach to the actin filaments and exert force on them to move.
This is what's going on right
This
now.
action is known as the sliding filament mechanism of muscle contraction. In this model, the sarcomeres shorten without the thick or thin filaments changing in length. A contraction begins when a bound ATP is hydrolyzed to ADP and inorganic phosphate. This causes the myosin head to extend and can attach to a binding site on actin, forming a cross bridge. An action called the power stroke is triggered, allowing myosin to pull the actin filament toward the M line, thereby shortening the sarcomere. ADP and inorganic phosphate are released during the power stroke. The myosin remains attached to actin until a new molecule of ATP binds, freeing the myosin to either go through another cycle of binding and more contraction or remain unattached to allow the muscle to relax. Muscle contractions are controlled by the actions of calcium. The thin actin filaments are associated with regulatory proteins called troponin and tropomyosin.
Okay, so we're now getting into more details. I don't want to go into this much detail, but that's basically how it works. So rigor mortis, when you die, is basically lack of ATP and fixation in a contractile motion. Okay, so There are many things that change with muscle as you get older. One of the major things that change have to do with energy production. This is a very energy dependent organ. And again, when it comes to energy, like we learned before in lecture 2, mitochondria. And you can already tell by the layout of mitochondria lining up between these sarcomeres. The message is very clear. It's geared towards energy production. So mitochondria change with age, which ultimately affect the function of the muscles to a certain degree. So something to think about in terms of aging muscle. There are several types of muscles. You can easily see during the Olympics, the marathon runners look very different from sprinters, right? That's because, also genetically, by training, they are enriching certain types of fibers that are more specialized for certain types of activities. So type 1 fiber is basically 2 types, which can be separated down more. But type 1 will be the slow contracting muscles, and has high resistance to fatigue. So used for aerobic activity, and you can use it for hours. Power produced is low, mitochondrial density is very high, and oxidative capacity is also very high because of the high mitochondrial density. Its major fuel source is triglycerides, fat. So if you're a marathon runner, you tend to have more enrichment in type 1 fibers. In the ultra elite athletes with the right genetic background, I've heard some muscles can be almost entirely type 1, which is amazing. Most people have a mix of both. And then the type 2s are considered the fast twitching muscles. So these are for sprinters, also for weightlifters, type 2, right? And here they use a different source of energy mostly. So their power production is relatively high. Mitochondrial density is relatively low. It's because their major fuel source is not fatty acids to burn, but more of local stored energy and glucose. Okay, so 2 different types of muscle. The question is, as you get older, do we see a decrease in one type of fiber type? And the answer is, we don't know. I've heard people say both things. So that's something to think about. Okay, so this is what it looks like. High mitochondrial content, which is for the slow twitching, long use muscles, look red because of high mitochondrial content, and white muscles are low mitochondrial, rapid bursts of energy. So weightlifting also. So, but mostly it looks like this. There's a mix of different fibers, unless you're a super elite athlete with years of training with the right genetic background. So how does muscle regulate glucose, if it is the major source? So if you eat a meal and there's insulin secreted, the major site of glucose clearance is your skeletal muscle. That is your major glucose uptake tissue type. And therefore, people say, we heard about exercise maintaining your bone mass, but also maintaining your muscle mass promotes glucose clearance. So if you have loss of muscle mass, relatively your glucose clearance capacity will decline accordingly. But the question is, what do we know about this process and how does it change with age? We know that insulin resistance goes up with age, right? So does exercise really help with glucose homeostasis in a condition where insulin resistance can be higher, basically aging? And the answer is yes. There are now studies showing that exercise can promote glucose uptake and clearance in a different method. So, for instance, when you go for a run, your muscles will need a lot of glucose, but your insulin doesn't spike to help that glucose be taken into the muscles, right? Nobody goes for a run and says, my insulin just went up really high because I needed to use it. What happens was, in fact, if you're on a chronic training regimen, your insulin sensitivity goes up, which means your insulin levels will go down in general. So what happens is the muscle is a very versatile machine where, yes, hormonally you can be stimulated to take up glucose, But because of the nature of its function, contractile motion, physical contraction can stimulate the muscles to increase glucose uptake mechanisms, independent of insulin receptors. And this is kind of the pathway. So underneath, inside the cell, a lot of the signal transduction pathways overlap. But the stimulation is completely different. And therefore, if you're diabetic and you exercise, there are papers, quite a few, showing that there's beneficial effects in glucose maintenance, even in diabetic patients too, if you exercise. So again, going back to insulin resistance and treatment with age, right? There's many ways to study. Because most of the drug development focus has been here, we're missing a lot of this target. And the only thing that we can say is do that. But then we can start to understand what it is about these mechanical problems or stress that allows the muscles to respond and take up glucose, right? So that's one aspect of muscle that's interesting that could be something in the future relevant to treating insulin resistance. But let me just say one thing quickly. The muscle, beyond the scope of this class, something to think about. Muscle is not just responsive to mechanical problems and hormones. It's one tissue type that is exposed to pretty much every type of stress you can think of. So when you exercise, you heat up. There's heat generation. And we know when there's a lot of heat, your proteins will denature and won't function properly. So the muscles during exercise have to also deal with heat stress. So that's integrated with exercise, which is integrated with mechanical stress. And so there's interesting research coming out nowadays, including ours too, unexpectedly, where you do something to modulate metabolism and make the muscle cells stronger by metabolically reprogramming them. Heat shock responses are very, very commonly found to be upregulated. Even though there was no heat applied, just by taking away or putting in more nutrients, the muscles react in an integrated way, right? But I've never heard of a drug target that's based on heat shock proteins. So that's another interesting thing. The mitochondria can reach 50 degrees Celsius when it's most active, which means it's a temperature that you will die if you reach as your body temperature. So there's mechanisms to counter that too. And then there's biochemical stress. A lot of blood going in means a lot of oxygen going in, which means a lot of oxidative stress. So the muscles also have to deal with that during exercise. So exercise seemingly is like a bad thing for your muscles. It's just exposing your muscles to a whole range of stress. Oxidative stress, heat stress, nutrient stress. Now you need to have more nutrients. There's mechanical stress, shear stress, which will change the shape of the cells, where the nucleus and everything will be like squeezed back and forth, and trying to do gene expression in a squeezed up nucleus is another challenge. There's all these problems that are combined that we don't really understand very well, that all change with age. So a lot of exciting venues there with skeletal muscle and aging in the sense of metabolic control. Okay, so how does the muscle use its energetics? Obviously, triglycerides for long term, and therefore you probably heard, anybody cyclists here? Anybody follow Tour de France? No? There's a lot of debate about what's the right fuel to feed the cyclists, because they can bike over 100 kilometers a day for many weeks. And so before that, it was all like carb and but more recently, it's a combination of fatty acids. So now if you are an elite endurance athlete, your chef will feed you complex mix of fatty acids. And there's a lot of research on this. And it's funny because I was in a meeting where they were discussing all this, and one guy came out, and a very well-recognized guy said, well, pistachios actually make it worse, but pecans or whatever makes it better. So there's a lot of debate of what to eat. But basically, your muscles can use fat for long term and glucose for short term, but there's also local storage in the form of creatine phosphate, CP. So basically, if you are being chased by a lion and you have to get up and run fast, you're not going to tell your fat cells to release triglycerides or whatever, your liver is not going to start making more glucose immediately. You have to use whatever's there fast to get yourself out of danger, and that is creatine phosphate, which basically helps regenerate ATP, and this has a provision for about 15 seconds. So that's like the immediate response. How many people take supplements for exercise? If you go to a USC bookstore, there's a whole shelf of stuff. I was so shocked, like, wow. And one of the things that the weightlifters eat is creatine phosphate. And they say, well, that gives you the last push to get that thing off your chest. And the idea is that it'll provide that local energy to give you that burst of energy. Again, scientifically very, very unstable. We don't know if that's really the case. Just because you ate more creatine does not mean it's going to be stored all in the muscle. But, you know, it sells. Okay, and then anaerobic glycolysis. Even without mitochondria, you can generate a lot of energy from glucose. So mitochondria will give you more energy for the same amount of food, but it's much slower than glycolysis, which will generate much less energy but very fast. So the anaerobic glycolysis is something that will help you generate a lot of energy fast. Okay, so if we lose muscle as we get older for many, many reasons, how does that work? How does muscle grow and repair and maintain itself? So the baseline is there are stem cells called satellite cells, and these are, they're not omnipotent. They can only become muscle cells normally. And these keep renewing themselves. And then when the signal comes in, they'll proliferate into muscle progenitor cells called myoblasts. And then they will feed into the fibers and become part of the fiber. And that's how you repair muscle damage. Okay, so the bundle of muscle fibers you saw in the video are actually a lot of these muscle progenitor cells fusing together to make one long cell. Okay? And senescence, cellular senescence, can now kick in the stem cell stage, which then decreases your ability to generate more muscle. And that's one of the aspects that contribute to loss of muscle mass with age. Progressive impairment. Okay? So, is this the video with that? So when you go work out and you are a weightlifter, you want to maximize your muscle growth. What you're actually doing is you're making micro tears in your muscles, and the growth of your muscle is the repair process. So you probably heard things like people saying, well, it's the actual recovery that's important after the workout, so you have to have sufficient resting for the muscles to grow. Which is basically true. So if you go and work out every single day without any resting period and put the same amount of stress or increasing stress in the same motion, the same type of muscle, your muscles probably won't grow very well. You have to move around the muscle groups, and that's why they say, what's a leg day, it's an arm day, it's a back day. What they're trying to do is to move around the muscle groups to let the damaged muscles repair while you train the other parts of the body. That's the idea. So you have to rest. So this is kind of how it works.
Muscles. We have over 600 of them. They make up between 1/3 and 1/2 of our body weight. And along with connective tissue, they bind us together, hold us up, and help us move. And whether or not bodybuilding is your hobby, muscles need your constant attention, because the way you treat them on a daily basis determines whether they will wither or grow. Say you're standing in front of a door, ready to pull it open. Your brain and muscles are perfectly poised to help you achieve this goal. First, your brain sends a signal to motor neurons inside your arm. When they receive this message, they fire, causing muscles to contract and relax, which pull on the bones in your arm and generate the needed movement. The bigger the challenge becomes, the bigger the brain's signal grows, and the more motor units it rallies to help you achieve your task. But what if the door is made of solid iron? At this point, your arm muscles alone won't be able to generate enough tension to pull it open, so your brain appeals to other muscles for help. You plant your feet, tighten your belly, and tense your back, generating enough force to yank it open. Your nervous system has just leveraged the resources you already have, other muscles, to meet the demand. While all this is happening, your muscle fibers undergo another kind of cellular change. As you expose them to stress, they experience microscopic damage, which in this context is a good thing. In response, the injured cells release inflammatory molecules called cytokines that activate the immune system to repair the injury. This is when the muscle-building magic happens. The greater the damage to the muscle tissue, the more your body will need to repair itself. The resulting cycle of damage and repair eventually makes muscles bigger and stronger as they adapt to progressively greater demands. Since our bodies have already adapted to most everyday activities, those generally don't produce enough stress to stimulate new muscle growth. So to build new muscle, a process called hypertrophy, our cells need to be exposed to higher workloads than they are used to. In fact, if you don't continuously expose your muscles to some resistance, they will shrink, a process known as muscular atrophy. In contrast, exposing the muscle to a high degree of tension, especially while the muscle is lengthening, also called an eccentric contraction, generates effective conditions for new growth. However, muscles rely on more than just activity to grow. Without proper nutrition, hormones, and rest, your body would never be able to repair damaged muscle fibers. Protein in our diet preserves muscle mass by providing the building blocks for new tissue in the form of amino acids. Adequate protein intake, along with naturally occurring hormones like insulin-like growth factor and testosterone, help shift the body into a state where tissue is repaired and grown. This vital repair process mainly occurs when we're resting, especially at night while sleeping. Gender and age affect this repair mechanism, which is why young men with more testosterone have a leg up in the muscle building game. Genetic factors also play a role in one's ability to grow muscle. Some people have more robust immune reactions to muscle damage and are better able to repair and replace damaged muscle fibers, increasing their muscle building potential. The body responds to the demands you place on it. If you tear your muscles up, eat right, rest, and repeat, you'll create the conditions to make your muscles as big and strong as possible. It is with muscles as it is with life. Meaningful growth requires challenge and stress.
Okay. So one last video quickly.
Muscle building. The key to building muscle is protein synthesis and cellular repair. Skeletal muscle is made up of long fibrous chains containing proteins. Bundles of thousands of fibers make up the muscle itself. When an athlete engages in a heavy workout, this structure is damaged, causing micro tears in the muscle fibers. The body naturally repairs this damage by mending the torn fibers. The result is a muscle that's larger and stronger than before. And with each additional workout, the athlete adds bulk, strength, and speed.
Okay, so it's for joints is use it and lose it. For muscles is use it or lose it. Very different, confusing messages for your skeletal muscular system. So let me throw this question. Why do we lose muscle mass as we get older then? What is the driving force? Yes? So hormonal, so endocrine roles, IGF-1, testosterone, growth hormone levels change, yes? Other confounding problems that could lead to muscle mass loss? Or should I say lack of muscle maintenance? Decreased activity, which is a catch-22, right? So social settings too. Diet, right? Proper eating. Sleep cycles change. Your repair mechanism goes down. What else? Mitochondrial changes. What else? Because So if we're trying to stop muscle mass loss with age, we have to understand where it's coming from to target it, right? Otherwise, the answer is always going to be the same: diet and exercise, right? Which is still true. That's pretty much the only way we can maintain it. What other reasons could there be? It's already the 3rd hour, so we're all falling asleep. But yes?
Inflammatory process within the body
Exactly.
that attacks
Yes.
muscle cells.
Yes, exactly. That's what I was getting to. So immune system. So how do you repair muscle? We heard the word repair. But let's talk about repair. How do you repair muscle? Cytokines that stimulate stem cells to proliferate and incorporate back into the muscle. Where do the cytokines come from? Blood? Immune cells, right? Why are immune cells in the muscle? Right, but why would they reside in the muscle? There are a lot of immune cells in the muscle, especially macrophages. So when you tear, you repair, and that's how you grow, right? When you tear, that means there's garbage made. How do you get rid of the garbage? Somebody has to come and pick up the trash. That's your immune cell, that's your macrophages. And they come and eat up the damaged tissues while new ones are being made. And while they're there, that's the activation signal for the immune system to recognize damage, and therefore they spit out cytokines, which is part of the signal for the stem cells to now engage in repair. So another layer added that we don't really understand very well is the immune aspect of muscle repair. How does that change with age, which we will see very clearly in the immune lecture. Our immune system changes dramatically with age. And how would that affect muscle? And not to talk about fat infiltration into your muscles, which fat itself acts as an inflammatory tissue. So that's a lot of complications here, right? Lots to think about. So cardiac muscle, I'm going to skip with a smooth muscle. Cardiac muscle, because I'm going to talk about it in the cardiac lecture, but smooth muscle, really quickly, this is what it looks like, and this is how they contract, and that's why you have a very more like a squeezing motion in your intestines and other smooth muscle areas. Involuntary. Okay. So let's finish up the lecture with some of the more prominent age-dependent changes to muscle. Loss of muscle fibers. And this I didn't talk too much, but I think I'll talk a little bit more about it in the sensory, or not the sensory, the neuro lecture. Another aspect that could lead to muscle mass loss is lack of usage. But that could be lack of usage, like you said, because of sedentary lifestyle, but also at the molecular level. There's not enough signal, or there's a problem with the delivery of the signal to the muscles from a neuronal aspect. The signaling part, that could change because your nervous system also goes down with age. So the nervous system, like we saw, that stimulates the muscle contraction, that connection is lost, which means the muscles won't be moving as much or as nimbly or as well. So the motor neurons at the spinal cord level, but also at the tissue level, could change, which could lead to loss of response. Reduction in specific types of fibers. Again, more recent data suggests it's more complicated. Infiltration of muscle with fat, which is not a good thing unless you're a Kobe beef. You don't want fat in your muscles. Reduced mitochondrial metabolism, but by reduced, I mean not just loss of energy production, dysfunction. Now we're talking about oxidative stress, which doesn't cause mitochondrial DNA damage, but definitely acts as a signaling molecule, which increases production of different metabolites, synthesis of metabolites, all changes, right? Let's see, and then this is some other stuff for another class. Okay, anything else that you can think of that changes with age in muscle? Yes.
I don't know how relevant the question is, but what happens when a person gets a stroke and now they don't have, is that like brain cells that are not functioning rather than the muscle?
Yes, so stroke has more to do with the brain damage. And I'll go through that in the nervous system lecture. There are different types of strokes and different manifestations of it. It doesn't happen in the muscles, but that's actually an interesting concept if you can apply it to muscles, actually. Muscle stroke. But it'll lead to atrophy because you can't use your body very well. Okay, so these are some of the evidence that your mitochondrial function goes down with age in the muscles. Your energy production capacity declines with age. I'm not going to go into details of what these measurements are, but basically one is measuring ATP production. One is measuring the activity of the enzyme that provides the energy, citrate synthase. Those all go down with age. Another enzyme that's part of your electron transport chain, those activities go down with age. And you can train and exercise periodically to slow down this process, even at the genetic level. So this is something called a RNA-seq, I believe, or was it a microarray? I can't tell. It's 2008, so it might be a microarray. Basically, an unbiased view of all the changes in the genes in a old sedentary versus young sedentary person and trained young and old people. So you can see the message here is that if you're sedentary and you get older, there's a greater change in metabolic genes compared to those that are trained, right? So there's less age-dependent changes. And endurance training appears to reduce this gap. Okay, so I'm going to skip on this. Okay, so sarcopenia. So let's say all fails and you weren't able to prevent that. At some point, you are going to reach a stage of muscle loss that becomes functionally problematic, so clinically problematic, and we call that sarcopenia, a degenerative loss of skeletal muscle mass, quality, and strength associated with aging. Happens around age 75, much faster. Can also speed up as early as 65 or as late as 80, depending on your lifestyle and your genetic makeup. Again, more common in females. A large part of this has to do with menopause. It's a factor in frailty, which is a more comprehensive conceptual approach to physical capacity with age, which I'll talk about later. Not today, I think. And which reduces the likelihood, if you have more sarcopenia, you are more likely to have falls, which would now lead to your skeletal structure and lead to fracture, which then opens the gate to pretty much all problems. Physically inactive people can lose as much as 3 to 5% of the muscles after age of 30, so everybody here is reaching that soon, or you're already started on it. And even if you're active, you still lose muscle loss. Although, and Young was talking about this in his lecture, an interesting thing, the comeback of all these superstars. So Arnold Schwarzenegger, Arnie, his photos were used for a while to demonstrate loss of muscle mass with age and increase in body fat, even for one of the most elite bodybuilders in the world. And there's a picture of Arnie when he's young and strong, and then after he's a governor, where somebody took a shot of him in the swimming pool somewhere where there's a big beer belly and loss of muscle mass. And then he quit being the governor, or he's done with that, and now he's back with another movie, and he's been training really hard, and he's almost back to the same stage as he was when he was shooting Terminator 1. So the question is, do elite athletes, the training you've done when you were younger, does that leave some sort of muscle memory that allows you to regain it easily when you're older? It's part of his story, muscle memory and training. Or is it really true that you can never go back? And I don't know if Arnie is taking anything that's not natural, probably helped by some chemicals. But the message is that it might not be as irreversible as we previously thought in the modern world, where nutrition is sufficient, medical support is sufficient, and the training regimens are much more scientific. There may be ways to maintain your physical capacity much better than we thought before, even if you start after losing that much later in life. So I don't know. This statement I think I have to rephrase with all these new studies coming out recently. You will have some loss. You're not going to be the same. But okay. Oh my goodness. Okay. Sarcopenia. This is what it looks like. Loss of muscle mass with age. Those are the driving forces. This is a video you can watch at your own time. It just basically explains the sarcopenia. And that's pretty much it for today. And my wife is calling me like crazy to pick up the baby. And I'm late. Are there any questions? Skeletal muscle? Okay, any questions with papers and all that? Not the exam, but finding papers and reading papers, email me or bug Ryan.
Give out the exam next week.
Next week is when I'll give out the exam, yes. Yes, or you can email it to me. You have to email it to me. All right, guys, thank you.